section 3.7, where we're going to be looking at rational functions. We're going to look at all kinds of different characteristics of those. First, looking at the specific reciprocal functions, and then we're going to evolve into doing some intercepts, asymptote, and to figure out where there are holes in our graph for other rational functions. So, in chapter 1, we looked at two functions in our toolkit. We didn't really do too much with them. First one being what we call the reciprocal function, which is 1 over x, and the other one being the reciprocal squared function, which if I square the top, I still get 1, but if I square the bottom, I get 1 over x squared. So, we're going to look at the graph of those. Now, you can actually do a t-table if you want, where you plug in some values, say, if I try to plug in 0, I get 1 over 0, which is undefined. That can't happen. If I throw in 1, I get 1. If I throw in 2, I get 1/2. If you do 1/2 that you throw in, 1 over 1/2 actually comes out to being a 2. So those common points, this one being the most one in particular, 1, 1, then at 2 we would be at 1/2, and at 1/2 we would be at 2, create kind of the look of that function in the first quadrant, okay? Now, if I try to do this with negative numbers, then the only difference that I have now is that all of these values are going to be negative, okay? So when we plot each one of those points, I get -1, -1, whoops, sorry, forgot that negative, then -2, -1/2, and -1/2, -2, and I get a graph that looks like this. So if you kind of keep plotting those points, then that's what it's going to look like. So it is a graph that is in quadrants 1 and 3. Now, if I have a negative version of this, so if I just do -1 over x, that is a reflecting over the x-axis. So this part that's in the first quadrant now will be in the fourth quadrant, reflected over the x. And the third quadrant will now flip up to being in the second quadrant. So that would be kind of the way the graph takes on for that. Now, let's look at 1 over x squared. Again, you can do a t-table if you want. I'm not going to do it, well, let's do the positive version of that. So if I throw 0 in again, that's 1 over 0, which is undefined. If I throw 1 in, 1 squared is 1, 1 over 1 is 1. If I throw 2 in, 2 squared, when I throw it in here, 2 squared is 4, 1 over 4 is 1/4. If I throw 1/2 in there, 1/2 squared is 1/4. When I do 1 over that, I get a +4. So I, again, have this 1, 1 that's a key point. Then here I have 2, 1/4, and at 1/2, we're now at 2. So what I have is this function that looks like that. And again, if you plot points at 3, 4, 5, you would see that they get very, very, very small. Now, if I try to throw in negatives, well, what happens when I square any number? If I throw in a negative in for x here, that means when I square it, it's going to become positive. So when I throw -1 in square gives me 1, 1 over 1 is 1. What's going to happen is that we actually have a symmetric graph here. At -2, I'm going to be at +1/4, and at -1/2, I'm going to be at +4. So I, again, create that look on the left-hand side. So we end up having that in quadrants 1 and 2. Now, if I look at the negative version of that, we end up reflecting both of those over the x-axis, so we end up having a graph that exists in the third and fourth quadrant. Okay? Now, the focus of 3.7 here at the beginning is to talk about asymptotes and places at which we have problems going on in our function. So, we're going to start with looking at the function f of x equaling 1 over x. Okay? So, can this function ever equal 0? Now, remind yourselves on fractions. If I have 0 over a number, that equals 0. If I have a number over 0, that is undefined. We can't do it. It's a problem. There will not be a value that comes out. So, will my function ever equal 0? Well, for a function to equal 0, the top has to equal 0. Well, is the top ever going to equal 0? And in this case, because I have a 1 there, no. Because the numerator will not equal 0 ever. Okay? So, y is not equal to 0, or, as we also say, our function value is not equal to 0. Hence, we will have a horizontal asymptote at y equaling 0. It's like a boundary, okay? And here I kind of describe what an asymptote is. It's a line that the graph approaches. Horizontal ones you can actually cross, but actually all the vertical ones you cannot cross. But horizontal ones could be crossed. But for our purposes, we're going to think of it kind of as a boundary that we're just approaching there. So we can look at the long run behavior. So in each one of these cases, as the horizontal, as x goes to plus or minus infinity, then our f of x does what? Okay, as x goes to plus or minus infinity, we're going to look at, if I go to positive infinity on my x, what happens? I get very, very close to that 0. If I go to negative infinity on the x, I get very, very, very close to 0. So that's what we want to throw down there in our line. Okay? So that means that we would have a horizontal asymptote here at y equaling 0. So we would have, change colors. Changing colors, that would be a y equaling 0. Okay? Now, second question. Can the function have an x value equal to 0? So again, we're starting with f of x equals 1 over x. And now we're saying, okay, my x value is 0. Is that okay? So, if I look at f of 0 and I throw 0 in, I get 1 over 0, which we just talked about. A number over 0 is undefined. So there's a problem there. There will never actually be a point there. So, no. Can the function have an x value of 0? No. X cannot equal 0 here. Hence, there is a vertical asymptote at x equaling 0. Now, looking at the short-term behavior of that, that means is if I'm going from 0 from the left, what happens to my f of x? And if I'm approaching 0 from the positive values or from the right, what is happening to my f of x? Well, let's look. If I pull back up here and I say, okay, what happens as I'm approaching, coming from the negative infinity, and I'm approaching 0, here's my x equaling 0, I'm approaching it from the left. Where are my y values going? They keep going, going, going to negative infinity. And as I approach on my function 0 from the right-hand side or from the positives, then all those y values keep going to positive infinity there for that. So we know f of x goes to positive infinity, and f of x here goes to, this one goes to negative infinity on the left, and this one goes to positive infinity on the right, constituting us to have a vertical asymptote for that function 1 over x. So we would end up now having a vertical asymptote there, symbolized by a dashed line. Now, likewise, we would also have a vertical asymptote here and a vertical asymptote here. So for both cases, we have a vertical asymptote of x equaling 0. That's that vertical line. And for a horizontal asymptote, we have y equals 0, which is this horizontal line. So those for both graphs occur in the same spot. Okay? So now it's kind of formally defined those horizontal and vertical asymptotes. So a vertical asymptote of a graph is a vertical line x equaling a, where the graph trends towards positive or negative infinity as the input approaches a. So as we are going closer and closer to that a value, that's where our 0 was, from the left and from the right, we went to positive or negative infinity. So as x goes to a, then f of x goes to plus or minus infinity. infinity. Now, a horizontal asymptote is a horizontal line y equals b, where the graph approaches the line as the input gets very large. So as x goes to plus or minus infinity, which is backwards from where our infinity was over here, then our f of x approaches that number b. And that would give us our horizontal asymptote. So for our 1 over x squared graph, f of x equaling 1 over x squared, then what happens? As we go to positive infinity, x goes to positive infinity, our f of x goes to 0. As we go to negative infinity, our f of x goes to 0. If I'm coming to 0 from the left, from the right, that means I go to positive infinity there, and from the left as I approach 0, it goes to positive infinity as well. So, long-term behavior is when I'm going to plus or minus infinity. So as x goes to infinity, then f of x goes to 0. And as x goes to negative infinity, then f of x goes to 0 as well. Short run behavior is as we approach that 0. As x approaches 0 from both sides, then in our f of x equaling 1 over x squared, our function value goes to positive infinity on both sides. Okay. All right, very good. Let's now talk about transformations of these graphs. So being able to move them left to right, up or down when we are graphing them. And this gets back to the idea of translating our functions. And so remember, if you are grouped with your x, that is your left or right, your horizontal transformation. We always had to take the opposite of what we were looking at. So this would tell me in the function 1 over that, so it's acting like a 1 over x function. We are going to go to the right by 2. And this number out to the end was our vertical shift. And we had to take the sign as is. So that means I'm going to go up by 1. Now, those original asymptotes are here and here with the key points of 1 or 1, depending on which quadrant that we're in, if it's positive or negative. But we're going to shift that now to the right by 2 and up by 1. So let's draw those. I'm going to get rid of these so they don't get confused. So if I shift it over to the right by 2, my new vertical asymptote becomes this. If I go up by 1, the new y equaling 0 asymptote becomes y equaling 1. So horizontal asymptote is y equals 1. The vertical asymptote is x equals 2. So what does our graph look like with 1 over x? Well, we had a key point of 1, 1 from kind of this new origin. And we're going to sketch it in the first quadrant. And -1, -1 was another key point on our original parent graph. And we're going to sketch that in the third quadrant because it is a 1 over x. Now, next piece here says that I have a -1 over x function. So -1 over x ends up giving me the transformation in the x direction and the transformation in the y direction. So here we're going to go left by 3 and down by 2. Take the sign as is on the number added or subtracted at the end. And then new axes or the new asymptotes, if we go left by 3, the vertical asymptote goes there, and down by 2, the new horizontal asymptote goes there. So we could also right now say, well, my vertical asymptote is x equals -3, and my horizontal asymptote is y equaling -2. And so now I'm acting as a 1 over x, but this time it's negative. So if you recall, go back on the other side, you should see that that is actually in quadrants 2 and 4. So -1, 1 would give me a key point over here. And over here, this would give me a key point to give me that graph. Okay, so all we're doing is sketching, kind of using the key points, 1 over and up or 1 over and down for your rational functions. Alright, the next two, hopefully you recognize the square now in each one of these. Notice that this one is negative, so a negative 1 over x squared took on the behavior where we were down kind of in the the third and the fourth quadrants. This with a plus 1 inside with the x means that's my horizontal transformation, and we would be going left by 1, and this one is up by 3. So left by 1 gives me a new vertical asymptote of that, and up by 3 gives me a new vertical asymptote here. And because I'm in quadrants 3 and 4, over from our origin, go over 1 and down 1 gives me to this side. And over 1, down 1 gives me that key point over there to guide me for the right side. And that would be my graph for this 1 over x squared. So vertical asymptote would be x equaling -1. Horizontal asymptote would be y equaling 3 here. And our last one of the graphs, then we're going to go and write an equation. This tells me I'm going to go to the right by 2 and down by 4. I have a square and it's positive, so it's acting like a 1 over x squared graph, which is in the first and the second quadrant. So to the right by 2 gives me a new vertical asymptote of x equaling 2. Down by 4 gives me a new horizontal asymptote of y equaling -4. Now, since it's in the first and second quadrant, this is acting as my new origin. Go over 1 and up 1 gives me that key point that we would do something like this. And this point here, we end up getting that part of my graph sketched in there to complete it. Alright, very good. So I said that was the last one, then we're going to go backwards, okay? So my recommendation is that you actually you draw in your asymptotes because that's what's driven into that function. Notice here I have this one that those are approaching, and here's the other one. So we've moved our axis over by 2, so left 2 and up by 3. So that's going to go in our function. I see that I'm in the first and the third quadrant, so that's acting as a 1 over x. And so now I think I'm ready to write my function. So let's go f of x. We need 1 over. Now, here we had to make sure that that was our horizontal shift. So we went left 2, but we have to take the opposite of what our eyes are seeing. So that should be a +2 inside there. And if I go up by 3, that means I'm going to add 3 at the end. Remember, that sign went the same as this one inside with the parentheses is the opposite. So this would be my function. On the next example, looks like a horizontal asymptote right here and a vertical asymptote that splits that right down the middle. So we have moved over 2 and up by, no, not 2, we went over 1. It's a half a scaling. Be careful there, that's a half a scaling. And we went up by 2. So to the right by 1, up by 2. Notice they're going in the same direction. So that's like a 1 over x squared, but they are reversed or flipped or reflected this time. So that negative out front symbolizes that I have a reflection. So I'm going to be looking at like that -1 over x squared. So to prep my function, we're going to go f of x equals, we need a negative. We also need something squared in the bottom to have them going in the same direction. And now we have to account for our going to the right by 1, which now goes into that parentheses as an x minus 1. And then going up by 2 gives me that +2 at the end. And that would be our final function. Okay. Alright, very good. Hopefully that's good. We're going to start looking at some rational problems, which could get a little intense when we're working with our asymptotes and such. But I'm going to kind of give you the why on some of these things, but notice that there's a process to each one of them on how to find those. Alright, so a rational function here is a function that can be written as a ratio. See that in the name? Whoops, not a ration. A ratio, which is in that piece right there of the name, of two polynomials. Call it p of x and q of x. Now, if it's a rational function, that means that we can divide each one of those or write it as a ratio or as a fraction. Now, basically, it's just a polynomial over a polynomial. So a sub n, x to the n plus, get us down to a sub 2x squared plus a sub 1x plus a sub 0. And I could do b sub n, x to the n plus, going down to b sub 2x squared plus b sub 1x plus b naught. Okay? So that's just basically a polynomial over a polynomial in our equation. Okay? Now, how are we going to find intercepts? We've found intercepts all kinds of times before, and now we're also going to look at asymptotes. So, given a rational function as part of investigating the short-run behaviors, we are interested in finding x and y intercepts as we have in the past in the horizontal and vertical asymptotes. We're going to save the horizontals for later, but for right now we're going to talk about y-intercepts, x-intercepts, and vertical asymptotes, okay? So let's start with a y-intercept. Just like we've done before, if we want to find the y-intercept, no matter what function that we're working with, we let x equal 0 and solve for y. If we want to find an x-intercept, that means we got to let y equal 0. And for a function that is a fraction, for it to equal 0, that 0 must be in the top. So we have to factor the numerator to find the zeros. Okay? Now, for our vertical asymptotes are places where I have undefined. So in a fraction, the undefined piece comes from the denominator. So therefore, if we are asked to find vertical asymptotes, we need to factor the denominator and set each one of them equal to 0 to solve for our zeros. And each one of those is written as x equaling some number. Okay? So here's our first example. Well, it looks like I have to factor the numerator and the denominator to find the x-intercepts and the vertical asymptotes respectively. So I'm going to go ahead and just factor this rational function. Notice I have a polynomial on top, polynomial on bottom. So I'm going to take that trinomial, break it down into two binomials. I'm going to split my x squared as an x and an x. Last sign is a plus, so they are the same that match the first. So a plus and a plus. And what do we multiply to get 6 that we add to get 5 would be what I asked the question of. And that is 3 and 2. Do the same exact thing for the bottom, although this time, I have a plus and a minus because the last sign is a minus. They are different inside. So I get a 3x and an x as I split that up. And I'm going to try the numbers of 4 and 4 to make that 16. So I have 4 and 4. Now, I don't know if I put the signs in the right spot. Remember, you have to check your outside and inside terms. Outside here is a minus 12x. Inside is a plus 4x. And looky there. I have a negative 8x. So I have the 8, but I don't have the positive 8 that I need right here. So if you have the same number, wrong sign, that means you just have to switch the sign. So a plus 4 and a minus 4 right there. Okay? All right, very good. Now we're ready to rock and roll to find our pieces. So we need to find the y-intercept. So we need to let x be 0. Now, you can let x be 0 in either one of these forms. I choose to find the y-intercept using my original form because when I throw 0 in there and square it, I get 0. When I times 5 by 0, I get 0. So the top, that goes away and that goes away, leaves me with just a 6. On the bottom, I do 3 times 0 squared, which is 0, plus 8 times 0, which is 0, minus 16, so that's gone and that's gone, leaves me with a negative 16 on the bottom, which reduces to negative 3/8 for our y-intercept. Now, if they ask you for the value, that's the value. But if they ask you for the ordered pair, remember that's when x was 0, so it would be 0, negative 3/8. That's the ordered pair. So either one, depending on which way they ask, is an answer. Okay, now let's talk about x-intercepts. X-intercepts, we want to let y equal 0. Okay, we want to let y equal 0. In order for that to be 0, we're focusing just on the numerator. Okay, so I'm extracting this numerator, and I'm going to use that down here for my x-intercepts. I need to know when x plus 3 times an x plus 2 equals 0. That's all I need to look at for an x-intercept. So I need to ask myself, what makes that 0? Well, it's negative 3. What makes that 0? Well, that's negative 2. And those would be my x-intercepts. Now, that's in a list form. But if they want it as an ordered pair, remember we set y to be 0. And we could write the ordered pairs as negative 3, 0 and negative 2, 0. So either one of those answers would work, depending on how they ask for it. And our last piece there is to find the vertical asymptotes. The vertical asymptotes, again, are ones that are driven by where the denominator equals 0, or where the denominator is undefined, okay? So 0 has to be in the bottom. So for our vertical asymptotes, I need to know where 3x minus 4, so we need to know that there, times an x plus 4 equals 0. So this one is nice, it's negative 4. This one, if you remember our trick, when we were factoring, we had to take the opposite of what our eyes were looking at over the number out front. So the opposite of negative 4 is 4. Over 3 gives me 4/3. Now, these are asymptotes, so they have an equation, x equals 4/3, and x equals negative 4 as our final answer. Now, you can say possibly there's an exception to every rule. Sometimes there is, sometimes there not. But here, there is. There is an exception to this rule. I'm going to look at this function, and I'm going to say, okay, I'm going to factor the top and bottom. Well, unfortunately, the factoring of the top can't happen because it's already factored down. But on the bottom, we actually have a difference of 2 squares, which yields a factoring of x minus 2 and an x plus 2. So you should know that from factoring. Now, if you notice these expressions, before I didn't have anything that is the same on top and on the bottom that I could cancel. But here, notice you have an x minus 2 and an x minus 2 that it can actually cancel and leave me with a final expression as a 1 over x plus 2. Okay? Now, what happens when, actually first, from an x plus 2, a vertical asymptote would be yielded as x equaling negative 2. What makes that 0 is negative 2. So we have a vertical asymptote at negative 2. We just graphed a couple of those where we would have this going on, and I end up having, a graph that goes like this and a graph that goes like that. But because I have canceled these x minus 2's, what happens in my graph is there creates a hole in my graph. It is undefined at x equaling 2. There is a hole at x equaling 2 in my graph. So if I were to come over here and I were to kind of erase a little portion of this, like here, put my axes back in, at x equaling 2, I'm going to have a hole in my graph. And it would just skip over it, and it would keep going. And so that is the difference, that when you actually have terms that cancel, that's going to create a hole. Everything left in the denominator would be creating a vertical asymptote. Irrational functions will occur where the denominator of the function is equal to 0 and the numerator is not equal to 0. Okay? Because the numerator wouldn't have anything on there. You're just looking at the denominator for vertical asymptotes. Now, a hole will occur in a graph of a rational function at the input, which is your x values, of expressions that cancel in the numerator and the denominator. So if they cancel, they create a hole. So let's look at this next function here. Next function says we need to find the intercepts, x and y, vertical asymptotes, and any holes within this function. So the first thing you need to do is factor. Well, we've seen almost all the other kinds of factors except for this top one here. Don't forget that the first rule of factoring is to take out any common terms first. So I'm going to take out an x and be left with a 2x plus 1 when I factor out that x. Now in the denominator, I end up having two binomials. Last sign is a minus, so they are a plus and a minus. I'm going to split up 2x squared as a 2x and an x. And the only factors of 2 are going to be 2 and 1. Now, was there anything common in the original? The answer is no. Therefore, there can't be anything common in these factors that I have right here. So if I try to do 2 in this first spot here, that's not going to work because I can't have a common factor there. So I'm going to put the 1 there and I'm going to put the 2 here. Now does that work? We must check our outside, which is negative 4x, and our inside, which is a plus 1. Therefore it does work. And so we need to now determine what happens in that function. So looking at the different expressions, notice I have this and that being the same. So I can actually break this back down as x minus 2 on the bottom and just an x left over on the top. So what happens right here when I cancel? Well, if those expressions cancel, right here we said we had a hole created at that point. So we are going to have a hole. Now, if you need to, set that equal to 0 and solve. But again, take the opposite of what you're looking at over that number. So we have a hole at x equaling negative 1/2. Where is our y-intercept? Our y-intercept, we need to let let x equal 0. Now, you can let x equal 0 here, 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 and here. Or you can let x equal 0 here and here. So if we do it that way, then I get y equals 0 over 0 minus 2, which is 0 over negative 2, which is 0. There's our y-intercept. Okay. Let's now determine x-intercepts. X-intercepts. Now, keep reminding yourself, x-intercepts are zeros. Where is a function 0? It is, for a rational function, it's 0 in the top. So I need to know when x equals 0. Well, it's at x equaling 0. So that would be my x-intercept. And for my vertical asymptotes, we are looking for the denominator where it is equal to 0. So there's my remaining denominator. I want to know when x minus 2 is 0. Well, what makes that 0 is when we have a 2. So therefore the equation is x equaling 2. And that would be your pieces that are requested for that function. All right, moving right along. There we go. All right, so now we get to this function. Again, factor first. Well, we've already factored the difference of squares, x minus 2 and an x plus 2. And when I factor the top, I need different signs, plus and a minus. Distribute your x squared to an x and x, and what do we multiply to get 6 that we subtract to get 1? Well, the only numbers would be 3 and 1. And I need a minus 1, so I need a minus 3 plus 2. And notice what happens. We have a common expression of an x plus 2. What does that create when they cancel? That creates a hole in my function at x equaling. Now what makes that 0? Negative 2. What is the y-intercept? The y-intercept is when x equals 0. Now what's our final function? Whenever I have those things canceled, that's what remains. So whenever you let x equal 0, you can put 0 here, 0 here, 0 here. All of those are gone, leaving us with y equaling negative 6 over negative 4, which reduces to 3 halves. Now the ordered pair would be 0, 3 halves, because we let x equal 0. Or you could put 0 into this function, and you could also get y is equal to negative 3 over negative 2, which reduces to 3 halves. Again, that would be the ordered pair for that y-intercept. Okay. What about x-intercepts? Our x-intercepts happen when the numerator equals 0. So there's my remaining numerator. Where is that 0? Now remember, we're actually letting y equal 0 here. Okay, when we're finding the x-intercept. So what makes x minus 3 0? That is when x equals 3. Now that would be as kind of a listing. As an ordered pair, we would do 3, 0 as our x-intercept. And then finally, we're looking for our vertical asymptotes. That is driven by where the denominator equals 0. And where the denominator equals 0 would be an x equaling 2. So set x minus 2 equal to 0 and solve, and that will give you your answer. Okay. All right. Now, when finding horizontal asymptotes, finding horizontal asymptotes would be where we are interested in the behavior of the function as the input grows large. So as we go to plus or minus infinity. So we will look at the long-run behavior, as what your book calls it, of the numerator and the denominator separately. Now recall that the polynomial's long-run behavior will mirror that of a leading term. Likewise, the rational function's long-run behavior will mirror that of the ratio of the leading terms of the numerator and denominator. So here are 3 different cases. First one we're going to look at is, and we need to remind ourselves that the degree of a polynomial is the highest power on each one of those. There's a degree, there's a degree, here's a degree, there's a degree, okay? So we're looking at each one of those as the highest power. So the degree for case 1 of the denominator, degree of the denominator, in this case is bigger than the degree of the numerator. So what we want to look at, talking about these leading coefficients, we don't care about anything else except for the lead terms. So I'm going to look at 3x over x squared. Now that is a fraction I can reduce. There's a common x that I can cancel out and be left with 3 over x. Now the question would be, as we go to our long-term behavior. So what happens as x goes to positive infinity? Well, if I throw a very, very large number in here and take 3 over that, you will find that the f of x goes very, very small, okay? And it goes and approaches 0, basically. So that happens in both cases. So as x goes to plus or minus infinity, then f of x will approach 0. Therefore, in this case, where your denominator in the bottom, or the degree, of the denominator is bigger than the degree in the top, you get a horizontal asymptote of y equals 0. That right there is my horizontal asymptote. Now, if we look at case 2, where the degree of the denominator is less than the degree of the numerator, then, wait a minute here. Yes, that's right. Sorry, I'm getting all flipped around here. I was looking at the top. All right, then I'm going to extract out the leading term, so a 3x squared all over an x, and again we have an x that cancels, but this time the x cancels up there, leaving me with 3x. Now, just look at the cases x goes to positive infinity. If I throw positive infinity in here for x, this number here gets very, very large. F of x goes to positive infinity. So, as x goes to plus or minus infinity, and if I throw a negative infinity in here, it'll go to negative infinity. F of x then goes to plus or minus infinity. Now, in this situation where they're both infinities, where the degree of the bottom is smaller than the degree in the top, there are no horizontal asymptotes. This is actually a case where we have what we call oblique asymptotes, when that numerator in the top is bigger. Alright, last case. We did the greater than, less than. Now we're looking at the degree of the denominator equals the degree of the numerator. So again, I'm going to extract out these pieces and get 3x squared over x squared. This time both of those cancel and leave me with a constant 3. So no matter how far that I go in the plus or minus, this number will never change. So as x goes to plus or minus infinity, in this case, our f of x is always going to 3. Therefore, our horizontal asymptote is exactly this. It is y equaling 3. Now, in layman's terms, how do we find the horizontal asymptote? You find a horizontal asymptote, you take the leading coefficient and you put it over the leading coefficient of the denominator as long as those powers are the same. Okay? So when we look at this first one, there's not a lot of work to be done. You just have to realize that I have to take the ratio of that, and I'm looking at the leading coefficients of both of those leading terms. So here, my horizontal asymptote would be y equaling 2/3. This is case 3, where our numerator and our denominator have the same degree. Now, this definitely doesn't have equal powers. But if you recall, there's not an x there, but technically I do have an x to the 0 power. Anything to the 0 power is 1. So I actually have a power of 1 in the bottom, power 0 on top. Therefore, the degree of the denominator is greater than the degree of the numerator. Hence, this is case number 1. If that's the case, if this is bigger than this, automatically you get y equaling 0 as your horizontal asymptote. No questions asked. That came from case 1. Alright, what do we have here? We have two terms now that have the same power. So we're back to case 3. And again, I don't care about that x cubed. All I care about are the numbers in front. So y equaling 5/2 would be the horizontal asymptote of that problem. So I didn't actually put one on here that kind of adds on the horizontal asymptote when you are doing problems like what we were doing here. But you can add that on. Okay, what would be the horizontal asymptote here? Horizontal asymptote would be the ones in front, 1 over 1, so y equals 1. So you can add that piece on to the problems when you're looking at the program. Alright, so the last two in this section is that we are looking for what is the equation of a rational function given these pieces of information, okay? Now we just talked about horizontal asymptotes. That's kind of the number out front, the ratio of that number. Vertical asymptotes, if you recall, are ones that were driven out of the factors in the denominator. And our x-intercepts was when y is equal to 0, but for a fraction to equal 0, that meant that our numerator had to equal 0, okay? So we're going to create a function, a rational function, so that in the denominator I need factors that give me zeros of -3 and 6. So what had to be in those parentheses that I kicked out an answer of -3? Well, if I throw -3 in, what do I have to do to that to get 0? I have to add 3. So x plus 3 had to be in there to kick out a negative 3. What had to be in there for a positive 6? Better have been an x minus 6. Now we do the same thing for our intercepts, except for now these factors for each of these numbers will go in the numerator. So what kicks out positive 4 as an answer? Well, we had to have a minus 4 inside there. What kicked out negative 6 as an answer? Well, I had to have an x plus 6 as my answer. And now the only last piece that I have to worry about is that horizontal asymptote for y equaling 6. If I were to go through and I were to FOIL this, I get an x squared and I get an x squared. So an x squared over an x squared doesn't give me 6 for my horizontal asymptote. It gives me a 1 with a 1 over 1. So somehow I have to incorporate a 6 there, and it's as easy as throwing a 6 in the numerator. So that will then give me a horizontal asymptote of 6. Alright, so that's the easier of the two. Now we get to the last problem in this section where we are looking at, now given the same information, here we have to worry about the factors in the denominator. Here with my x-intercepts, those are coming from the numerator, but now we have a y-intercept of 10. Now remember, that's when x equals 0, so I have the point 0, 10 there in the skies. Now, just like we put that 6 out front, I'm going to do a placeholder here as an A. Okay? That's kind of like when we had our parabolas and stuff. I need a number out front to create that horizontal asymptote, or in this case, to create a y-intercept of 10. Alright, so let's start with our denominators for our vertical asymptotes. What has to be in the bottom for negative 4 to be an answer? Better be a plus 4. What has to be in the bottom for negative 1 to be an answer? It better be a plus 1. Likewise, for our intercepts, we need to now do our factors in the top for 1 and 5. We would need an x minus 1 and an x minus 5. So that's kind of our preliminary equation. But now we have to determine A by giving the last piece of information, which is 0, 10 for my y-intercept. So that's an x and a y. I have x and y right in here. This is my y that I can replace 10 and 0 in to find A. So that's what we're going to do. I'm going to put 10 in for y. I'm looking for A, but all these x's now become 0 because I'm using the x-intercept, or excuse me, the y-intercept to determine A. Okay? So, it's kind of a little bit of a mess here. I get 10 on the left. This is negative 1 times negative 5 gives me a 5 times A all over 4 times 1, which is 4. Now, there's multiple ways to do the solving of this equation, but the easiest would be to do the reciprocal to solve for A. So you can times by 4, then you would end up dividing by 5. But if I times by 4/5 to start with, those cancel and those cancel. So I would multiply over here by 4/5 as well. Now, this leaves me A on the right-hand side, and 5 goes into 10 twice, creating an 8. Therefore, A is equal to 8. So our final answer, all I'm going to do is put 8 back in for A. It would be f of x equals 8 times an x minus 1 times an x minus 5 all over an x plus 4 and an x plus 1. And that's our final answer at this point. Okay? So I know that's a long section. There's a lot of information in there, and there's actually a lot of information that I didn't give you. And we're just going to kind of touch on those rational functions at this point with that piece. So until next time, where we're going to be looking at inverse functions and radical functions. And we've kind of looked at it in Chapter 1, but we're going to revisit it with different functions. So until next time.